Apart from that, we need to ensure that this is plane strain fracture toughness. So, and there is going to be a transition from plane strain to plane stress as the, so this is not a good drawing. ये क्या बन गया? Okay, so this is your compact tension specimen. And what have I done? So I have removed a little bit from the crack plane. समझ में आ रहा है? So if I draw it from back side, then it will look like this. Okay. So from both sides, I have removed some material and I've created a notch. Why have I done this? तुम तो sit through कर रहे हो.
Sir, I know the reason.
I know, that's right. Saurabh, बताओ. Why have you done it? This is called side grooves because these are grooves on sides. Okay, so why do we do it? बताओ.
So that crack will remain on the same, मतलब on that groove plane only. It will not distract to
So
the.
how do you ensure that by making this?
Sir, क्रॉस सेक्शन एरिया डिक्रीज किया है और जो अमाउंट ऑफ स्ट्रेस अप्लाई किया है, स्ट्रेस कांस्टेंट है, एरिया कम हुआ तो
एरिया कम हुआ तो स्ट्रेस ज़्यादा होगा उसमें.
हाँ, तो क्रैक उसी डायरेक्शन में प्रोवाइड करेगा.
ठीक है, समझ में आया नहीं? Cross sectional area has decreased, right? So for the same amount of force, stress is going to be higher on that plane, right? On this plane, okay? So this plane must be aligning with the crack front. If it is not, then how do we make it? So whenever we do any testing related to fracture toughness, one thing you have to make sure is that the crack must be a sharp crack. Okay? It cannot be a notch. It must be a sharp crack. How do we make a sharp crack? What is a sharp crack?
YRD.
Yeah?
Using YRD.
Using wire radium you could. So this is English stress concentration factor for an ellipse. Okay? So this is two-way and this is two-way. Right? So what will be the value if the B goes to 0? If B goes to 0, what will be the value? Infinite. Okay? So as long as you have a finite root radius, you are not going to achieve the asymptotic stress behavior on the cracker. Asymptotic behavior of Irwin's formula will be achieved only when you have a sharp crack. If it is not sharp, then the stress will have a finite value. Okay? So then how do we make a sharp crack? How do we make B equal to 0? So wire medium you will be cutting by a wire. So wire will have a radius of its own. So how do we do it? Do you understand the question? We have to make a sharp crack. How do we make it? कैसे बनाएं sharp crack?
फटीग से भी नहीं बनेगा।
तो पॉसिबल ही नहीं है। तब तो बंद करना पड़ेगा पढ़ाना, possible नहीं है।
टूल ही कोई ऐसा चाहिए मतलब।
कोई भी टूल होगा वो तो फाइनाइट होगा ना, any tool will be finite, so then how will you make a crack which is that sharp? So that is done by fatigue, by loading it under cyclic forces, and then a crack initiates, and that crack is initiating not because of any tool, that crack is developing because of fatigue damage. Okay, so then you will have a hairline crack. Okay, and then you are supposed to make a little bit of crack. Okay, so one possibility was that you make this rectangle with holes, and then you create a notch here, and then you do it in fatigue loading and create a crack from here to there, which is sharp all along, but we don't do it. Okay, suppose you want to have, and usually, and this is also very important, that the K1C testing must be done under a range of A by W. Okay, so this must be somewhere between 0.45 to 0.65, 0.6 or so, not more than that. It has to be in this range. So suppose, and mostly people try to achieve 0.5. In that case, thickness will be equal to crack length, both of them will be smallest, so then you can follow that criteria. So A by W is equal to 0.5, so that means A naught is equal to B naught. So if suppose your B is 10 millimeter, then W becomes 20 millimeter. Okay, so then crack length you want to achieve also will be 10 millimeter. You want to achieve 10 millimeter for starting your test. Okay, so you will make a notch of 9 millimeter. That's your call. How much fatigue you want to do and how much fatigue you should do. Okay, so you will make initial crack length of 9 millimeter, sorry, notch of 9 millimeter. So this tip is at 9 millimeter, and then for 1 millimeter you will do fatigue cracking. Okay, that is called fatigue pre-cracking. Why pre-cracking? It is a crack, but it is a precursor to the fracture toughness crack. You follow? So there will be another crack which will develop when we do monotonic loading, and from there we will calculate K1C. So this crack is an initial crack which is sharp for the theory to be valid, so that we can do our K1C testing. Okay. So why don't we do this complete cracking via fatigue? Why are we making a notch for the maximum amount of distance, and then for a very small amount we do fatigue cracking? Why do we do that? फटीग एक ही डायरेक्शन में होगा ना, नॉच तो है ना. We are beginning with a notch. Complete rectangle नहीं है, so I can make a notch here, and then I start fatigue. So crack will, probability will be, unless you have a lot of inhomogeneity in the material, fatigue crack will develop there. Notch भी तो stress intensify करेगा ही ना. So then why don't we do that? Why don't we do that?
Sir, I think in that case fatigue loading will not be possible.
Why not?
Sir, because notch is very small, and sir, that compressive load might not possible, sir.
Why not? मैं टेंसाइल सैंपल में कंप्रेस कर सकता हूँ, तो नॉच में क्यों नहीं कर सकता?
सर फटीग से सरफेस पे भी लोग भी क्रैक आ सकते हैं।
सरफेस पे ही क्रैक आएगा फटीग से, and the notch front is surface. तो वहीं पे तो क्रैक लाना है, और ये आर्ग्यूमेंट तो बाद में भी एग्जिस्ट करेगा for 1 millimeter और. So the real reason is time. You will need a lot of time to create a crack which is 10 millimeter long in comparison to 1 millimeter long. You will have some frequency of loading, right? 10 hertz, 50 hertz, 100 hertz. So 100 cycles per second. And how much time it takes for a metallic material to develop a fatigue crack. So initiation of a fatigue crack, so the first step of the fatigue crack takes 10% of the total lifetime the material has. The other problem is you cannot do fatigue pre-cracking at a very high stress levels. Okay. So whatever you do, you can't be really in the high cycle fatigue region. You can't, because there is a notch. So there will be a plastic zone. Okay. So somewhere it will be in the low cycle fatigue region. So stresses are going to be high, but you are not supposed to have the stresses very high. Why? Yes, it will. आगे बोलो.
The notch will not be sharp.
No, it will be sharp. So when you do fatigue loading, you are stressing it, and then, so let us say you are going in tension fatigue. So you go to 500 megapascal and come back to 200 megapascal. So this is the kind of fatigue you are doing. Okay. So what will happen during loading? So when it reaches 500, what will happen? There will be a plastic zone, because that part is monotonic, right? And when you come back to 200, the plastic zone size will decrease, and then it will increase. It really cannot happen, because once the thing is plastically deformed, it cannot be undone. But the active plastic zone will be smaller at 200, larger at 500. Right? So suppose in the first cycle you create a plastic zone, okay? And suppose now that the material has a yield strength of 500 megapascal. So what will happen? You have just created a plastic zone, right? It has crossed 500. It has just achieved 500. So you have a plastic zone. Then you come back to 200. What will happen? You will have another area which needs to plastically deform, and this deformation will be happening at the next yield point, right? Because there will be strain hardening. So once which has plastically deformed will further deform at higher stresses and not at that stress. So you follow what I am saying?
Sir, 200 पे नहीं होगा ना plastic zone?
नहीं, 200 पे नहीं होगा, पर नॉच पे स्ट्रेस जाएगा आगे ना, because of this.
जैसे 500 पे नीचे
हाँ,
वो plastic
डिफॉर्म हो गया.
उससे नीचे elastic पे
उसके नीचे इलास्टिक regime है,
तो जैसे 500 200 में लेके आएंगे.
पर 200 में स्ट्रेस बढ़ेगा टिप पे. This is sigma applied. This is 200. So the stress will be higher at the tip of the notch, right? So it might cross yield strength, but if it crosses 500, there will be no plastic zone. It has to cross more than 500. Do you understand? So the plastic zone, the consecutive plastic zone radius will be smaller, because this sigma naught is increasing for strain hardening material. Do you understand? For a plastically deformed region, the next sigma naught is higher. So plastic deformation starts here, and for the material which has plastically deformed, further deformation can happen only at higher stresses. It cannot happen at this stress. You can't have more strain than this. Okay? So when you do, and so there is a plastically deformed region, and this plastically deformed, and suppose now that you are applying a fatigue cycle which also goes in compression. Okay? Or you can take another example, that you want to do fracture toughness testing at minus 20 degrees Celsius. Okay? So the sharp crack which you will be making, that you will not make at -20. That you will make at room temperature. Okay. So what happens when the temperature goes down? The yield strength increases. Right. So this plastically deformed region, which is created in the fatigue pre-cracking stage, is deformed at certain value of stress. As you go down, your yield strength is increasing in temperature. As you go down in temperature, yield strength is increasing. So this deformed region will act as if there is a residual stress in the material. Okay, so it has already strained. So this will try to close the gap. Okay, so for monotonic loading, you need to have a plastic zone at least larger than this. It cannot be smaller than this. Do you understand? When you are really doing the K1C testing, you have to apply such a load so that the plastic zone which forms because of monotonic loading during the K1C testing must be larger than the plastic zone which you have created during fatigue pre-crack.
Yeah.
If the plastic zone during monotonic loading, that size is smaller than fatigue pre-cracking, then it is not really K1C testing because you are not testing the real material. You are testing a plastically deformed material. Do you understand? Whatever is happening in the deformed material, not in the real material to begin. Okay? So you have to ensure that monotonic loads are always higher than the fatigue stage loads. In order to ensure that, you must be doing fatigue pre-cracking at forces or stresses much lower than the yield strength of the monotonic condition. Okay? So if the yield strength of the material is 500 megapascal, you should never go to 500 megapascal to do fatigue pre-cracking. You should go to 200 max. There is a formula for that in the standard, how larger you can go, and initially this formula was stress based. Now this formula has been updated to stress intensity factor. So previously, in the previous versions of standards, they used to say that the sigma which you are applying, sigma max, must be some fraction of the yield strength of the material. Now they are saying that the stress intensity factor which you apply in fatigue must be smaller than percentage of stress intensity factor you achieve in your K1C testing. Okay? Is it okay? So we create this pre-crack so that it becomes sharp. Okay? And fatigue pre-cracking is also done in mode 1. Fatigue pre-cracking is monotonic crack extension under cyclic loading. And we know that when you apply cyclic loading, things will damage easily. Right? In high cycle fatigue, what happens? A material can break even at forces which are elastic. Right? Or wrong? Right? You have, so high cycle, so your SN diagram looks like this. Right? What is the real difference between low cycle and high cycle fatigue?
लो साइकिल में मतलब स्ट्रेस होता है वो लेस स्ट्रेस पे फटीग होती है
किससे लेस?
एंड्योरेंस लिमिट्स कोई
एंड्योरेंस लिमिट के नीचे तो कुछ होगा ही नहीं.
हाई साइकिल फटीग एंड्योरेंस लिमिट के नीचे होता है मतलब जैसे स्ट्रेस कम रहेगा वो लेफ्ट हैंड
एंड्योरेंस लिमिट के नीचे अगर होगा तो फेलियर ही नहीं होगा. You cannot make SN diagram. What is the meaning of endurance limit? That for infinite number of cycles, the material will not break. That is your endurance limit. Right? So if you are testing at endurance limit, then for infinite number of cycles you will have no failure. That's the definition of endurance limit. तो तुमको कोई point ही नहीं मिलेगा इसका अर्थ. तुमको infinity पे point मिलेगा. This is n, no? Number of cycle for failure. So where will you get your point? At infinity. तो कभी नहीं बनेगा.
सर लो साइकिल फटीग में स्ट्रेस एम्पलीट्यूड का वैल्यू हायर रहता है
कितना हायर, कितना लोअर?
यील्ड स्ट्रेंथ
Yes. So low cycle, high cycle fatigue में difference ये है that in low cycle fatigue stresses are higher than leading. So you have plastic strain there. Baskin's law and low cycle fatigue is related to plastic strain. Okay, we will discuss that fatigue also. And In high cycle fatigue, stresses are lower than sigma naught. So here, the applied stress sigma max is lower than sigma naught. इसका क्या मतलब हुआ? इसका मतलब ये हुआ कि your maximum stress is also in the elastic region. Why is it breaking? It shouldn't. All the strain should recover, no? It is going to be elastic deformation. So why it is breaking? You know? Failure तो impossible है इसमें elastic है ना? Elastically deform हो ही नहीं रहा है, सीधे ब्रेक कर जा रहा है, कैसे? ऐसा कैसे हो रहा है?
So the stress amplitude देंगे sigma max sigma min.
Sigma max is not going beyond sigma naught, so amplitude कितना भी क्या फर्क पड़ता है?
Because plastic strain is always there. जो आपने बताया था.
देखो तुम्हारा ये आ सकता है. Plastic strain is always there. That is correct. That is correct. And people have done experiments. Okay. And people have done experiments by doing testing at stresses lower than sigma naught and stopping at certain value of number of cycles. Very, very marginal number of cycles. 100 cycles, 10,000 cycles, 1,000 cycles. Okay, which is nothing for metallic materials. Okay. So at those number of cycles, when they looked at the microstructure, what they found was slip bands. What are slip bands? Slip bands are collection of slip lines. What are slip lines? Slip lines are the steps which are formed by dislocation when it reaches the surface. Okay? So you can't really see one slip line, you see accumulative slip lines, and those slip lines were visible on the microstructure. So it might have come because of polishing, right? So you do some heat treatment or something so that that part is gone, or you do electrochemical etching or polishing so that you don't really enforce any strain on the surface. And then what happens? Some of the slip bands disappeared, but some of them retained. They did not disappear. So that was a signature that, and those slip bands were not in all the grains. They were in some grains. Okay? And those are called persistent slip bands. Why? Because they persisted.
Yes, please.
So even stresses lower than yield strength under cyclic loading, people found that dislocations are moving, plastic deformation is happening, not in all the grains, but in some grains they are happening. Okay? So plastic deformation can happen even below yield strength. Fine, that we'll discuss later when we discuss fatigue. So we made this fatigue pre-crack, and then we make this groove on the sides. We remove the material from the side, and there are some geometry in this. So you have to maintain certain angle here, okay, and you have to maintain certain distance, which should not be larger than 5% of the total thickness. So by doing this, one, that we ensure that the area, so the plane on which the crack front is, crack front basically is a line, it's not a plane. Okay? So suppose this is the tip of the sharp crack. Okay, so in 3 dimension it will look like this. So this is a line, right? So when a crack initiates, it can go in any direction. Why would it be perpendicular to the force applied? Because of the stress situation. So it will have more probability to be perpendicular to the force applied in mode 1. Okay? But there might be scenarios that you have some inclusion, you have some manufacturing defect. Because of that, you have created high stress region in certain other direction. So crack might go in other direction. Okay? If your A by W is very small, if your A by W is less than 0.45, in that case, it is under plane stress situation, whatever is the thickness. It doesn't matter, it's a shallow crack, your in-plane constraint is too small. Okay? So what happens in reality? You have a pressure vessel, you have some aircraft body or whatever components you have. The cracks which appear on these things, they come not because of manufacturing defect, because you have a lot of quality check during the manufacturing process. So you have whole protocol established that you are not supposed to have a defect larger than this. If it is there, you reject that component and you take one. So you are ensured that there are no defects. The defects which really come in pressure vessels, aircraft probably because a bird will hit it, a debris will hit it, okay, and that will be a marginal scratch, a very small scratch, and that scratch will have a by W of 0.1 or less than that. That's a very shallow crack. Even then we are doing it in an extreme region of 0.5 A by W, because first it will ensure the conservative design criteria. So the worst condition, then you will say why not 0.6? Why 0.5? Because beyond 0.5, so in that range, properties really don't change. What happens beyond 0.65 is a different game, and not much experimental data is there. Okay? So as I said, beyond 0.6, what will happen is that, so suppose your crack front is here, so then this dimension and this dimension will become equivalent. Okay? So a lot of people say that constraint is lost, constraint decreases, and a lot of people say that constraint increases. I am in the favor of constraint increment, but there is not so much experimental data to prove it in the literature. You can do modeling, but modeling alone will not prove anything. Okay? So we create this side groove 1 so that we create a plane on which this line can propagate because the stresses will be higher. Other reason is, if for some region the thickness is so that you have this kind of sigma z. So obviously at the surface it will be 0 and it will be increasing at the center, but if it is plane strain, it should be something like this. If it is really plane strain. Okay? But if you have this kind of profile, then it's a combination of plane stress and plane strain. Okay? And by creating a notch is also a crack. By creating notches on the surfaces, I am increasing the stress here because there will be a plastic zone here also. There will be a stress asymptotic behavior if I create a notch on the sides. So I am elevating stress by creating these side grooves. Okay? So the stress which was going down, sigma zz, is sigma yy for the side grooves. For this crack, the stress which is in the thickness direction is actually the stress in the perpendicular direction to the crack. Okay? So that is going to increase because of this crack. And then the stress profile will change, probably to this. And then you will have plane strain all around. Okay? So that's another reason why you do side grooving. So side grooving must be done after fatigue cracking, not as per your convenience. कि जब मर्जी आया तब कर दिया. Because once you make a side groove, you will not be able to see the fatigue pre-crack which you will be developing using any microscope. You can't really plant an SAM on fatigue machine. So you usually use either your eyes with a polished surface on metallic materials, or you put an optical microscope, low resolution optical, low magnification optical microscope. And side groove, because you have cut it, it will be shining and you have a line. You are supposed to have a line, but it will not be a line because you will be making it with wire EDM or some other cutting tool. So it will be reflecting too much and you will not be able to see if the crack is really along that plane or not. Okay, so first you are supposed to make the fatigue pre-crack, Then you are supposed to do the side grooving. So I have this sample, I have made fatigue pre-cracking, so I can see where the crack is. Okay, so from here I will take theta by 2, and I'll ask some vendor or myself to cut it. So that I ensure that the tip of this side groove lies on that plane of the crack tip. Okay? Then how much time do I have? 12:30. ठीक है.
20 minutes.
20 minutes है? Good. So we don't really need to discuss how do we measure the crack extension, because in K1C we don't do that. So when it comes to crack growth extension, we'll discuss how do we do that. But in this case also you need to have a check on crack growth. Because if the material is brittle, you will not have too much of ductile or slow crack growth. You should have flat fracture. Okay? So you should have brittle fracture. Very less amount of ductile tearing, or it is also known as stretch zone, which is not really a ductile crack, but it's the plastic zone which is deformed heavily that appears at the crack tip on the broken sample. So after breaking your samples, you are supposed to look at it under stereo microscope, which will have a higher depth of field. So because the fracture surface will have some roughness. Okay. So optical microscope will not work because you need a flat surface, right, to have the focus on it. So you need a stereo microscope which has a range of focus, and there you can look whether you have ductile tearing or not. If it is significant ductile tearing, your K1C test is not good. So don't use that value. Okay. You can also, so these things are to check. So in the data you are seeing that XS is less than 1/4 of XP, and even then you see that there is huge amount of ductile tearing. That means something is wrong. Okay. So now let us talk about a special case. So Weibull is a very famous name in fatigue. Okay. And in 1951 he writes a paper, and I don't really remember the title of the paper, but it is somewhat like a statistical function of great importance, something like that. Okay. And that function which he created, he also showed that it could be used for yield strength of Bofors steel, it could be used for the strength of fibers in rice, and it could also be used for the case which we are going to discuss. Okay. So what he explained was that if you have a chain, then how do you say that this chain has failed? You have a chain and you have n links in it. This is 1, 2, 3, 4, 5, n. When will you define the failure of this chain? तुम्हारा भी कुछ grade आ सकता है. Yes, correct. Okay. And if the probability of failure of one of the link is exponential of some function, then probability of non-failure of this link would be 1 minus p. So that will be 1 minus exponential of this. And if you have n number of links, how will you define the survivability of the chain? By non-failure of all the n links. कोई भी link टूटा तो chain टूटा, कोई भी नहीं टूटना चाहिए. Correct? So that will be 1 minus p to the power n. That will be 1 minus exponential of right? And he also gave the phi function, which is a very simple function, which is equal to x minus xu to the power n divided by x naught. What is x naught? These are some statistical things. X naught is a reference value. Okay? And xu can define the failure, the property from which you are defining the failure of the link, for example. So let us say that you want to say that the material property which will be dictating the failure of the link is ultimate tensile strength. So xu becomes ultimate tensile strength if and x becomes the stress. If the stress goes beyond xuts, then it will fail. If it is less than that, it will not fail. Okay? And x naught you can calculate by statistical analysis. Okay? So, in a brittle material, it is assumed that the fracture, so first assumption is that fracture can happen only after plastic deformation. There must be some amount of plastic deformation. Without plastic deformation, fracture cannot happen. And if there is a crack, there will be plastic deformation. You can't stop it. Okay? So, that means there must be a minimum value of, there must be an xu. Okay? You can't have fracture at zero stress. कुछ लगा ही नहीं, अपने आप टूट गया, तो कोई कीड़ा लगा होगा, ऐसे तो नहीं हो सकता. That will be corrosion. Okay? Otherwise, it cannot be x to the power n by x naught. That cannot happen. Right? That is impossible. And so you are assuming that there will be a plastic deformation and then there will be fracture. Okay? So the probability of fracture must be proportional to the plastic deformation. Must scale with plastic deformation. Right? And then, so let us try to quantify the plastic deformation in a very simple way. So plastic deformation, I can say, I can measure it by the plastic zone radius, right? And plastic zone radius is 1 by some pi by sigma naught whole square. Okay? And this K1C we don't know. We don't know because this K1C is a variable. It varies for the same material. It varies. And I will tell you how it varies. But whatever is the K1C, this will be the plastic zone radius. Okay? So this area, assuming it to be a circle, which it is not, but it is a small because it is a brittle material. So my approximation will not be that far, even if it is ellipse or some other shape. Okay? So then it becomes pi r square is the area. So then you have pi gone. So you have some constant and K1C by sigma naught whole square. What happens to this? This is r, so this will become to the power 4, right? Alpha square is same thing, it's a constant. Okay? What will be the volume?
Okay.
Another assumption that it is plane strain. So I am assuming that the plastic zone is not changing along the thickness.
Okay.
So I extrude it throughout the thickness. So the volume becomes thickness into area. Cylinder. Okay. So then you have B alpha K to the power 4. Sigma naught will be a constant because that's a material property. So it scales with, so suppose it is not reaching to K1C. Whatever K you apply, there will be a plastic zone. So the plastic zone is scaling with this, and then the volume, the probability will be scaling with this because it will be dependent on the volume which is plastically deformed. Okay? So the probability of failure I can write as 1 minus exponential of some function of bk to the power 4. Okay, and then I need to modify this according to this equation. So I can write it as probability of failure is equal to 1 minus exponential minus whatever k I am applying. So if I just keep k naught here, then it becomes 2 parameter Weibull distribution. And if I introduce k naught minus k minimum in the denominator as well, then it becomes 3 parameter Weibull distribution. Okay. So this is also a similar format of that, where x naught is also reduced by a value, which is the minimum value. So x naught minus x min. Okay. So this would describe the probability of failure for whatever value of k you are getting. Okay, and k minimum you have to approximate, and rest of the things you have to find from the statistical analysis. Where do we apply this? So one thing is sure that this is applied in brittle fracture. Okay, and in BCC alloys, if you calculate K1C at different temperatures, so minus 160 and so on, what do you think the profile will look like? How do you think it will look like?
Increase.
Don't look at the equation. Think about the reality. It's a BCC material. It's a steel, ferritic steel. Okay?
Increase.
And ferritic steel is going to, so you are doing testing at different temperatures. Right? So as temperature increases, ductility increases, you should think that the toughness will increase. Right? Or wrong? It will increase. So when you do the testing here, if you do n number of testing, you will get different values. Then you do testing here. Then you do testing, let us say here. So what are those circles? Those circles are one test. So what is happening here? It is not acting as a material property. So you get different values for different specimens. Why is that happening? Same material, same temperature, same thickness, same dimension, same machine. एक ही टेम्परेचर पे एक वैल्यू नहीं है मेरे पास. Okay, and this is not that this is 20 and this is 20.5. It's not. It's 20, it's 60, it's 180, this is 300. Okay, so the fracture toughness which you think is coming at 0 degree, you are also getting at minus 120 degree for one sample. Why is that happening? Why do you think is that happening? सोचो और बताओ.
डिफेक्ट्स में वेरी
तुम ले ब्रेड लो आज खत्म करो तुमको एग्जाम में नहीं होते हैं. Okay. So Landis and Schaffer, I don't remember the year. Landis is one guy which you will, if you are really in the region of fracture toughness, you will hear him, read him a lot. He is alive. I don't know for how long. He is really old, but he has done really great work. Okay, so Landis and Schaffer, everyone observed this. Not in terms of K1C, but this phenomena was known for impact energy, Charpy test. If you do Charpy test, you also get same profile of impact energy. Okay, and this Charpy test was the solution for the liver tissue failure, which they did not do. They overlooked at the probability of fracture at lower temperatures. Okay, so what they found was, suppose you have a crack front, and crack front is really not straight. We will discuss in some class why it is not straight. Well, one reason is that you don't have complete plane strain situation. Okay, so if the stresses are higher, wherever they are higher, constraint is larger wherever, the crack will propagate more because it doesn't have any possibility of flow. Okay, if too much constraint is there, then it must break. Okay, so constraint is largest, highest in the center, so the crack propagates not uniformly, it propagates more in the center, less at the surface. So you get a tongue kind of shape. Not exactly also like this. In experiments you will see something like this. Okay, it's not that uniform. So crack front is represented by this line, and assume this to be a broken sample, a broken Charpy sample, fracture sample, whatever it is. Okay, and a crack, so plastic deformation happens, and then there is a trigger point, and then it breaks. Right? This trigger point, this amount of critical K1C will differ if you have some things which can increase the stresses because of their presence, and those things can be carbides, can be infusions. Right? In ferritic steels you will have carbides, a lot of them. You will have a lot of infusions. They are oxides, so they don't have really that much amount of ductility. So if a stress is applied, they break. Once they break, there is no void formation. There is a separation. Continuum has been broken. If the material surrounding it could stretch, then it will become a void. If the matrix couldn't stretch much, then it will act as a very small crack, micro crack. Okay? So all of these broken particles are stress raisers initially, and once they break, they become micro cracks. All of them. Not all of them. Depends at which temperature you are doing. Okay? So some of the particles will have a tendency to turn into voids. Some of the particles will have a tendency to turn into micro cracks. Depends at which temperature. So how much is the ductility of the matrix material? It depends on that. Okay? So let us say that all of them can change to micro cracks. If you have on the crack front 1, 2, 3, 4, 5 number of these particles, in comparison to a situation where you have only one particle, this will break first, that will break later, because the increment in local stress created by 5 particles will be more in comparison to one particle. The local stress increment by a cluster of particles of 5 will be more in comparison to 5 distributed particles. This contributes to the probability. I will have n number of samples, and not all of the samples will have same amount of carbides distribution at the front. Okay? And nobody can control it. Okay? So you are going to have one sample where fortunately you made a crack front where there was no carbide, and then you created by unfortunate events a sample where, so this is just random. Okay, there might be some countable distribution to it, but for now we take it random. It is a random distribution. Okay? If you have grain boundary and you have Cr23C6 type carbide, then those carbides have a tendency to nucleate, grow, so precipitate at the boundary. Okay? So that's really not that random. Okay? So that should be a function of grain size. But those kind of works have not been done, so it is assumed to be random, and because of that you have distribution at every temperature. You have statistics to play. Okay? So there is a thermal part associated with the fracture, there is a athermal part associated with the fracture. And we will continue from this in the next class.